In this video lecture, we're going to go over several features of the basic feedback system, or the feedback control system. As we've seen in class already, a plant function might be given by some transfer function g of s, which has inputs and outputs, inputs u of s and outputs y of s. And so we define those over here. When we look at the transfer function from the inputs to the outputs, then we can write down that the open loop transfer function TOL of s is y of s over u of s, which we defined as being g of s. And remember, the transfer function for a system is the impulse response of the system and then take the Laplace transform of that. If we want to go ahead and look at using control to achieve some objective, then we first need to close the loop. And what we mean by closing the loop is taking the output y of s and feeding it back, maybe through some filter h of s or some other transfer function, and comparing that to some reference signal. In this system, we have the forward path, which is the path that takes us from the sum junction all the way to the output y of s. And then we also have the feedback path, which takes us from y of s back to the sum junction. These two paths will become important as we look at different types of architectures. We, of course, define the reference, r of s, as the reference input, or the command, or that's really our objective. H of s we define as the feedback transfer function, and it allows us to modify the output and then compare it to the reference signal. And of course, we use the sum junction here, and we use a negative, so we have negative feedback. Finally, we also define L of s, which is g of s times h of s, the product of these, the plant and the feedback transfer function. We define that as the loop transfer function. And this transfer function is going to become important when we do analysis in the root locus domain or the Bode plots in the frequency domain. Finally, using the feedback rule, we can calculate the closed loop transfer function, now that I've closed the loop, which is the transfer function defined as taking from the reference input r of s to the output y of s. And we go ahead and calculate that using our simple feedback rule. Notice the loop transfer function shows up in the denominator here of the closed loop transfer function, and the denominator is just 1 plus the loop transfer function. This again is going to become important when we do root locus analysis. The next thing we can do is look at what we call unity feedback and then series compensation. And this is the type of architecture that we've been using a fair amount in class so far. So the first thing we do is get rid of the feedback transfer function h of s, and we assume that it's just a unity gain. So we can just replace it with a single block, or in this case, nothing. And we just feed y of s straight back to r of s and compare. Next, we put a controller in series with the plant, and we call this series compensation. Compensation here is just another word for control. Now, once we've changed the system to unity feedback system, we go ahead and we add a series compensator. And what this is we add another transfer function in the forward path, which is in series with the plant transfer function g of s. So finally, we generate an error, e of s, which is the difference between r of s and y of s. We feed that through our control law, or our compensator, c of s, which then generates an input to the plant, which is u of s. Notice in this case, the assumption is that r of s and y of s have the same units, and when I compare those, I would generate an error. If y of s did not have the same units of r of s, we could always add a gain here, which would convert units, or we could add another transfer function if needed. Finally, we can calculate the closed loop transfer function for the unity feedback system with series compensation. And notice it looks very similar to the unity feedback system before, but here L of s is just g of s, and the transfer function, the compensation or the control law c of s shows up in both the numerator and denominator. Finally, we'll look at several typical control architectures. This architecture is known as feedback compensation. And as with anything, depending on the application, you might choose one architecture over another. In this architecture, we're using feedback to generate. In this architecture, we're using the output of the plant, and we have a feedback compensator, or control law, but there's also an outer feedback loop, which compares the reference to the actual output of the plant, which generates the error. This architecture is also known as inner loop control and is often used for aircraft or autopilot designs where the feedback here is actually working on, say, aileron position, but the actual reference might be pitch angle. Full state feedback is something that we're going to look more at towards the end of the course when we look in the time domain or the modern control theory. In this case, the state is a little bit different, x of s, than the output of the plant, and we'll have to try to understand exactly how that works. But assuming we had all of the states of the system, say position and velocity, but the plant output was only, say, position, we would take position and velocity, feed that through a gain k, and then use that to compare to the reference. The difference between those is not exactly an error, because an error would be, say, r minus y. But that signal, u of s, now is the input into the plant. Full state feedback works very well if you can measure all of the states. If you can't measure all of the states, there are ways around this using what we call a state estimator or observer. Again, we'll look at that in the 8th week of class. There's also series feedback compensation where we have essentially a feedback compensator, but then we add a control law C of S into the forward path of the control architecture. This works well if we need to modify the error that's being fed in to the plant with the feedback compensation. There's also something known as forward compensation, and in this case we have forward compensation with series compensation. So here's your typical series feedback, unity feedback compensator or control law. But then notice we also have this transfer function C sub f, which filters or acts on the reference. So in this case, this could be a simple gain, which might convert units, or it might be something that does something, a transfer function that does something a bit more complicated, say like take a derivative or take an integral or something, some sort of filtering process on the reference input. Finally, we might use what we call feedforward compensation, where we take the reference signal and we feed it forward of the feedback loop, and we use a control law C sub f, which acts only on the reference signal, and that gets added in to the output of our typical series compensator or control law, which is acting on the error. Notice C of S acts only on E, the error, while C sub f acts only on the reference. And then the sum of those two are added and fed into the plant, and then we can look at the output to generate our error. This is typically used in what we call set point control, where we're trying to get y of s to go to the final value of r of s, but for some reason we need to filter this value reference r of s and then add it into the input to the plant so that things will scale appropriately. In conclusion, as with a lot of things in this class, the architecture you choose will depend on the application that you have. And you'll typically get slightly different results depending on what kind of architecture you choose, but two or more architectures might be sufficient or might actually work for you.